Welcome to the continuing lecture in basics of machining. Now, let us try to see the effect of these angles. So, this is the rake angle. So, now it is called as positive rake angle, it is called as negative rake angle, and it is called as neutral zero rake angle. So, machining strong or brittle materials, smaller rake angles are used. So, that means to say positive. So, brass and other material we try to choose 0 or positive rake angle. If the tool material is brittle like ceramic and carbide, negative rake angle is used. So, if the tool is brittle, why in brittle means what happens? There are already several cracks. Brittle like ceramics and carbides, negative back rake angle have to be provided because they want the tool to be stronger, right? Because in ceramic cracks can be easily done, you will give a larger depth of cut. While providing negative back rake angle, energy required to overcome the friction increases, which increases the overall power. So, when we use a negative rake angle, the power increases because there is large area of contact, right? This is negative, this is 0, this is positive. So, when you have, there is more contact of the tool to the workpiece. If that is the case, then you will have lot of power required. But negative rake angle are required for tool stability. So, when you do a depth of cut, you will try to have a stronger tool. Otherwise, due to impact, the tool might break. So, here if you try to see the tool life with back rake angle, there is a maxima at one point. The tool life increases and then it reaches maxima and then it tries to reduce. So, back rake angle has an influence on the tool life. Machining ductile material, tool life increases by increasing the back rake because of decreasing the contact length between the chip and the tool over the rake face. So, when I said positive, this is what is positive. So, here what is happening? You will have a sharp edge and the amount of material in the tool is also reduced, right? But when the angle becomes more than a particular value, the lip of the tool decreases. This decreases the strength of the tool. So, the back rake angle for ductile materials are generally chosen between 10 to 15. When we talk about side cutting angle, it is the angle between the side cutting edge and the line extending the shank. Side cutting edge, if you go back, you can see the angle is measured in a plane parallel to the base. So, here the feed represents uncut chip thickness and depth of cut represents width of the chip. Here the feed represents the uncut chip thickness and the depth of the cut represents the width of the chip. So, two things. So, here what we have is the temperature is directly proportional to the root of true feed or the feed rate, whatever it is. So, here if you see the side cutting edge angle, again it follows a same trend wherein which at one particular angle you have a maximum tool life and then you have a reduction in both the sides. So, now let me introduce the terminology F and D. F is called as the feed, D is called as the depth of cut. Depth of cut means it is the, when you try to machine an object or a workpiece, your tool is pushing from this side. Perpendicular to the axis of rotation, whatever you give is called as the depth of cut. So, here it was original, D original, and this is D final. Okay. So, now the difference whatever you call, this is called as the D, which is called depth of cut. When we move along this direction, along the axis of rotation if we move, so that is called as the feed. So, the tool, this is the tool, right. So, I will make a tool here. assuming that this is a tool, the tool which moves along the axis is called as the feed rate. This is called as a feed. The feed will be always defined as feed rate. So, feed rate will be defined as mm per revolution or mm per minute. So, why is that mm per revolution there? Because the workpiece rotates at a given RPM. So, you can try to see what will be the advancement of the tool along the axis of the part, in one revolution. Other way around. So, this is declared as RPM, revolutions per minute. We can also try to find out mm per minute. So, once we put revolution or minute, it is called as feed rate. If that is not there, it is called the feed. The feed can be 0.2, 0.3 millimeter. When we put with respect to rate, 0.2 millimeter per revolution, 0.3 minute per minute, you can try to say. So, the feed what we define here is the true feed or the feed experienced by the cutting edge in perpendicular direction, and it is equal to the uncut chip thickness. So, uncut chip thickness is there. So, we will see in detail what is chip thickness, uncut chip thickness as and when the lecture flows. The cutting process. There are two types of cutting processes. One is called as orthogonal cutting. The other one is called as oblique cutting. So, the video which runs here is a representation of orthogonal cutting. The cutting edge is straight. The cutting edge is straight. So, the tool, this is the tool which moves here. The cutting edge is straight. It is not angled. So, this is cutting edge is straight. So, cutting edge is straight parallel to the original plane surface at the workpiece and perpendicular to the direction of cut is orthogonal cutting. So, the cutting, this is called as the cutting edge. This is the tool cutting edge. It is at 90 degrees to the workpiece. So, parallel to the original plane in 2D at the workpiece and perpendicular to the direction of cut is orthogonal cutting. So, examples of orthogonal cutting will be shaping. We will see that later. So, this is the schematic representation. If you want to express it in 2D, it is given here. So, now you can see here the feed, what I discussed in the previous slide is given here, and this is called as the depth of cut. Oblique cutting, where the cutting edge, this is the cutting edge. The cutting edge is at an angle. The cutting edge of the tool is inclined to the line normal to the cutting direction. In actual machining like turning, milling, etc., cutting operation are always oblique cutting. So, this is the angle and this is the feed which we have defined. Right. So, if you see both the figures, you will clearly understand this is orthogonal cutting and this is oblique cutting. Look at the cutting edges, look at the cutting edge here and look at the cutting edge here. Right. This is oblique cutting. In reality, it is always oblique cutting, but for simplification in the measurements and other derivations, we always assume it to be an orthogonal cutting. So, now let us see the difference between orthogonal cutting and oblique cutting. In reality, all the cutting majority of the cutting process falls under oblique cutting. In orthogonal cutting, the cutting edge of the tool is perpendicular to the direction of the cut. Here it is inclined with the normal to the direction of cut. The chip flows over the tool face and the direction of chip flow velocity is normal to the cutting edge. So, chip flow over the cutting face. The chip flow over the cutting face. So, this is cutting, this is the tool, the chip flows. This is the chip which tries to flow. The chip flows on the tool face, making an angle with the normal to the cutting edge. The chip flow making an angle to the normal. The cutting edge is longer than the width of the cut. The cutting edge, you see here, it is protruding. It is longer or larger than the cutting, the chip, whatever it flows. The cutting edge is longer than the width of the chip. What is the width of the chip? Width of the chip is this. This is called the width of the chip, W. So here the cutting edge may or may not be longer than the width of cut. The maximum chip thickness occurs at the middle. So when the chip flows, when you try to take a cross section, the maximum, suppose you take a cross section, the maximum of the chip would be in the middle. So this is a chip cross section. Right? The tool is perfectly sharp and it contacts the chip on rake face only. Only two components of cutting force acts on the tool. They are mutually perpendicular to each other. The tool life is less because the chip is completely in contact and it is perpendicular to the cutting edge. So all these things lead to these 3 points. The tool is perfectly sharp because the cutting edge is normal and is contacting the chip at the rake face only. The two components, when you try to resolve it, you will have only two components. One is the thrust component Ft and the other one is the radial component Fr. So you will have only two components. They are mutually perpendicular to each other. The tool life is less since the chip always moves on the rake face. It is less. So when we go for oblique, the frequently more than one cutting edge is in action. 3 components come because since it is at an angle, so you have to resolve Ft and Fr. You will have an angle component. So you will try to have cutting force Fc, Ft and Fr. You will have 3 forces acting on it. The tool life is larger than the orthogonal cutting. So this comparison tries to give you a better understanding about orthogonal cutting and oblique cutting. The machining conditions. So generally these are the conditions which is set in the machine. So this is called as the depth of cut. You can see depth of cut which is defined here. The feed, whatever I have discussed earlier, feed is given here. Depth of cut is discussed. Now the speed is the rotation with which the workpiece rotates. So these are the 3 parameters which are process parameters set in the machine. Process parameters set at the machine. So the other environment can be lubricating because there is going to be a metal to metal contact, there is friction. So friction will generate heat. So the heat has to be cooled down and the friction has to be reduced. So we add a coolant or a lubricant which is an environment around the cutting process. The presence of oxygen in the atmosphere, it will try to react with the nascent surface and form oxides. The third thing is the temperature. At the cutting zone, the temperature is very high. So these are the 3 environments which are going to play an important role. As we saw in the first course, when the temperature is applied, there is a softening of the material. So if you can apply heat prior to cutting, so then it softens the workpiece, and moment it softens the workpiece, your forces will go down. So this talks about the temperature. Then the last one is talking about the work holding, fixture, jig, chuck and collet. The collet, whatever we saw, was put on the tailstock. You can also have it in the headstock. Chuck is holding for the device. There are 3-jaw chuck and 4-jaw chuck. Jig is basically to guide the tool. Suppose you are trying to drill from the tailstock. So then you have to guide the tool. Then we call it as a jig. If the workpiece is to be held, we call it as a fixture. So these are the work holders and two holders. The cutting speed V is primary motion. The speed at which the work moves around, the speed at which the workpiece moves with respect to the tool is called as the cutting speed, which is V equal to pi dn. F is the secondary motion. Primary motion is the speed. Secondary motion is the feed, and then comes the depth of cut. So heat dissipation in chip formation. When we try to take an orthogonal cutting and when the tool is perpendicular the cutting edge is perpendicular to the chip moving, or if the chip moves. Okay. So, here we are discussing about the orthogonal cutting. In orthogonal cutting, the cutting edge is straight and this is the workpiece. So, now the chip moves on top of the rake face. So, when the chip moves on top of the rake face, it is metal to metal contact. So, there is going to be friction. The friction what happens while the chip moves along the tool creates a heat phenomena. So, it is not only here the heat phenomena, it is also along the shear plane. It is also along the shear plane there is going to be the heat. So, this is called as the primary heat zone and this is called as the secondary heat zone. The maximum heat happens at the primary heat zone and the compared to primary, lesser heat happens in the secondary heat zone. The chip formation during machining operation leads to the distribution of heat during the cutting operation. The chip formation in the machining occurs due to shear deformation. So, this is the machining happens only because of shearing. So, the shear happens. So, that plane is called as the shear plane. Due to shear deformation of the workpiece as it interacts with the tool surface. There are three major heat distribution zones. One is primary cutting zone, secondary cutting zone and a very small tertiary cutting zone. Primary deformation happens along the shear plane. The secondary deformation happens along the chip tool contact area and the third one happens between tool and workpiece contact area, which is very small. So, primary deformation zone, secondary deformation zone and work tool contact zone. In primary deformation zone, 70 to 80% of the heat is dissipated. This is because of plastic deformation of metal. What is shear? Shear is this action is shear, right. So, the shear is the dominating phenomena for cutting here. This is because a plastic deformation happens at the shear plane. About 20 to 25% of the heat is dissipated between chip and tool contact surface, and the residue whatever is the balance goes through the tool workpiece contact. So, after machining the workpiece will also be hot. Why is it? It is because of the tertiary deformation zone happening here. So, the total sum has to be 100. So, accordingly there will be only 1 to 5% happening in the tool workpiece contact. The chip temperature will be phenomenally high. The chip formation mechanism. The shear plane is the region where plastic deformation occurs before the material gets separated as chip. So, here is the shear plane. This is the shear plane. So, the shear plane is the region where there is lot amount of plastic deformation. This plastic deformation allows to go further and form a chip which gets separated from the workpiece. The effectiveness of the chip formation depends on the shear plane angle, that is called as the shear angle. It depends on the shear angle. So, what is the shear angle? Phi is the shear angle, which influences the shear angle, influences the chip thickness. What is chip thickness? This is TC. TC is the chip thickness. Cutting force. While cutting, there is a force which is encountered during this process. So, cutting force, from that cutting force derived power. So, the effectiveness of the chip formation depends on shear plane angle phi, thickness of the chip, the force for cutting and the power consumption. A higher shear plane angle generally reduces cutting force and improves machining efficiency. When is the higher shear plane? The angle is going to be higher. when phi is large, you will have reduced cutting force and which improves efficiency. Shear plane high, then forces are less. Because the forces are less, the power is also less. Force and power are directly proportional. When the force is high, the power also will be high. As the cutting tool moves at a cutting velocity v, what is v? v equal to pi d n. As the cutting tool moves with a cutting velocity v, the chip flow along the rake face of the tool at a velocity of vc. So, the chip what exits out goes through a velocity called as vc. So, the rake angle will be this is called as the rake angle. The rake angle plays an important role which helps in determining the chip formation characteristics. So, if you look at it, we have taken an orthogonal cutting process. We have drawn the schematic of an orthogonal cutting process. We have seen the shear angle, then we have seen the chip thickness. So, prior to chip thickness, whatever is there, the feed, whatever we call it as, this is T naught. It is called as uncut chip thickness, and people also counter argue the chip itself is not formed. How can you call it as uncut chip thickness? So, this is called as T naught and this is called as TC, right. So, TC is the chip thickness. And you should understand it is a constant volume process. Whatever was the material here will also come out. If the chip thickness is large, then the width will reduce, right, because it is a constant volume process. You cannot add or delete material here. It just goes like that, right. It extrudes. It is almost like an extrusion. So, we saw the influence of chip thickness, we saw cutting force and power consumption. We also understood what is cutting velocity and chip velocity. Chip velocity is Vc, and for cutting which angle plays a very important role is rake angle. So, you can make the rake angle positive, negative or 0. So, that means to say if it is positive, so if this is positive, when it is negative, the rake angle will be something. This will be the rake angle. This will be negative rake angle, and in the in between center you will have positive. So, you will have positive rake angle, negative rake angle and 0 rake angle. This is what we saw in the prior slides for discussion. So, the large rake angle facilitates the large rake angle. So, this is large, right. So, this is positive. So, positive large rake angle facilitates smoother flow of the chip, isn't it. So, you have a tool, the chip moves. So, now you reduce the angle of that tool. So, now the chip easily will flow. The larger rake angle facilitates smoother cutting, reduces cutting force and improves chip flows. While a smaller rake means you are moving from positive towards 0, a smaller rake increases tool resistance and leads to higher power consumption. So, this is what we discussed in the previous slide, saying that the force and power are directly related. The rake angle has influence on the cutting force and the chip formation. The lower value of R, what is R? R is the chip thickness ratio. What is chip thickness ratio? T naught by Tc is called as the chip thickness ratio. The lower value of R indicates higher deformation and greater energy consumption. So, now you can see this. So, what is T naught? Where does this T naught come from? T naught come from the process parameter, whatever you make it on the machine. So, the chip thickness ratio will be R equal to T naught by Tc, where R is the chip thickness ratio, T naught is the thickness of the chip prior to the formation is T naught and Tc will be there. So, if Tc is very large, let us take a value 1 by 2, 1 by 4, assuming I am just putting 1 by 6. If Tc value is large, assuming T naught is small, then the ratio will start reducing. The chip thickness after separation is Tc. The general chip thickness after cutting is always greater than before. So, the chip thickness ratio will be always less than 1, because there will be, you are measuring only the thickness, you are not measuring the width, the thickness, because here it is a, as I told you, it is only an extrusion process. Whatever is the material here, this material goes there. So, the material when it flows, it tries to spread. So, the thickness can go low, the thickness cannot be higher than T naught. So, the geometry of the orthogonal cutting model allows us to establish an important relationship between the chip thickness ratio, rake angle and the shear plane angle. So, we have seen only these three. So, what are we seen? We have seen R, we have seen the rake, we have seen phi. Now, I am trying to establish a relationship between them. Why? Because if I establish a relationship, I can try to figure out what will be the material property which I should use such that I control the machining process. So, if you see here in this orthogonal cutting diagram, we are trying to establish a model which allows us to have a relationship between chip thickness ratio is R, then you have rake angle alpha and shear plane angle phi. So, let us try to take the length of the shear plane angle, length of the shear plane angle as Ls. Shear plane, this is shear plane, the shear plane angle, the length is Ls. Following the substitutions can be made, T naught equal to Ls into sin phi. You have to use all the graphs, or this is rake angle, this is shear plane angle. So, this is phi and the shearing operation happens. So, because of that the severe plastic deformation, the chip is getting formed. So, now I try to take a small triangle, I try to draw the small triangle into this. So, this is the thickness of the plane. So, what is this is a thickness, right, plane or a plate. We will try to assume it as a plate, right, or a plane, whatever it is. You try to take it as a plate. Plate means a small thickness. So, thickness of the plate. So, now you are trying to, this is a triangle which is drawn A, B and C. I zoom this and I present it here. So, I have A, B and C. I try to draw a normal which is D. I know the angle between A and B, the angle between AB and AC, this angle is phi. And I also know the angle with which it is tilted. So, this normal I draw, it is BC and this normal is trying to represent alpha, which is the rake angle. Now, when I draw a normal B which intersects at AC will be D. So, this angle what it creates is phi minus alpha. Now, I try to draw a relationship. T naught is equal to Ls into sin phi and Tc is nothing but Ls into cos phi minus alpha. This is alpha. Thus, it is alpha. Thus, R is what is R? T naught by Tc, which is Ls sin phi by Ls cos phi minus alpha. So, now this becomes, when we try to rearrange all these things, we get sin phi divided by cos phi minus alpha. So, this can be rearranged to determine phi as the following: tan phi is equal to R cos alpha by 1 minus R sin alpha. So, this tries to tell me a relationship between shear plane angle, cutting chip thickness ratio and the rake angle. And why is it important? Because this will in turn try to dictate my force and that in turn will try to dictate my power. So, that means to say the smooth flow of the chip. The following definition of shear strain in metal cutting can be derived from this: gamma is equal to tan phi minus alpha plus cot phi. And why is this important? Because the shear strain can be calculated by doing a universal tensile testing test. You can try to do and get this relationship. Okay, can I measure phi? No, it is not possible practically. Alpha, can I measure? Yes, alpha is you who set this rake angle on the tool. Can I measure R? Yes, R is nothing but TC is the output, what you give in the process parameter. So now the chip formation factors, these are the factors: cutting speed, feed rate. Higher cutting speed and smaller feed rates promote continuous chip, while low speeds and large feeds causes discontinuous chip. We will see continuous chip in the upcoming slides. So the continuous chip will always try to have a lower power. Discontinuous chip will try to have a improper surface finish. Tool geometry and rake angle. A sharp tool with a larger rake angle reduces the cutting force, improves the chip flow and enhances the surface finish. The workpiece material and the shear angle. The ductile material forms continuous chip. Brittle ones produce discontinuous chip. And a higher shear angle reduces the chip thickness. Higher shear angle reduces the chip thickness, which is TC. Friction, cutting fluid and built-up edge. Proper lubrication minimizes friction, reduces tool wear and prevents built-up edge formation. Chip breaker and depth of cut. Breaker prevents the long tangling chips, the continuous chip, while the depth of cut affects the chip thickness and the cutting force. The machine stability, temperature and vibration, these are all machine related parameters. A rigid setup, controlled temperature and minimal vibration improves chip control and surface quality. So these are the factors which help in chip formation. The actual chip formation we will see. It should be noted that there are differences between the orthogonal model and the actual machining process. We said all the models what we explain here are orthogonal, but in real time it is all oblique. First, the shear deformation process does not occur along a plane, but it occurs along a zone. So in the previous case, just for simplicity, we took it like a plane. Right, we took it like a plane. So here, for simplification of model, we took like a plates. There are a series of plates, and then these plates are moving, or series of cards. These cards are shearing. So then we took a card with a thickness. But in reality, it is not going to be a plane. It is going to be a zone. So then it is called as shear zone. So since it is first happening, it is called as primary shear zone. First, the shear deformation process does not occur along a plane, but across a zone. If shear were to take place across a plane of zero thickness, it would imply that the shearing action must occur instantaneously as it passes through a plane, rather than over some finite time period, which is in reality, why do we always consider it as a plane? Simplicity. But in reality, it is a zone, because if you try to take it as a plane, it has to be formed instantaneously, but there is a small lag in time while cutting happens. The second is in addition to the shear deformation that occurs in the shear zone, another action happens along the chip back end and the tool. The addition shear is referred to secondary shear to distinguish itself from the primary shear. The secondary shear predominantly is friction based, and that is why what we do is we try to have discontinuity here. So when we have discontinuity here on the tool, it is called as chip breakers. So this chip breakers, what happens is, will try to shear off the secondary deformation zone, and that leading to discontinuous chip. The third, the formation of the chip depends on the type of material being machined and the cutting conditions of operation. So there are three zones: primary zone, secondary zone and the tertiary zone. So these are the chips which we were trying to talk about. Types of chip: it is continuous, discontinuous, continuous with built-up edge and serrated one. So here if you look at it, when you try to take a ductile material and proper choosing of rake angle and other process parameter, we might get a continuous chip. And when we try to machine polymer, the chip continuously runs for even a kilometer. That means to say, without break, it keeps on be going. Those chips are called as continuous chip, predominantly seen in ductile material. So discontinuous chip, when you have a chip breaker or when the material is brittle. In brittle material, what happens? There are already several cracks which are there in the workpiece. So as and when you start machining, the cracks initiate and move faster, and it tries to join at a place and it tries to remove as a chip. So you always try to get discontinuous chip. So the discontinuous chip can happen because of brittle material, and the rake angle can be negative, and improper choice of process parameters can lead to discontinuous chip. Right? In discontinuous chip, there will always be vibration in the machine, so which will lead to poor surface finish. The third one is going to be continuous chip with built-up edges. As I told you, there is lot of friction which is going to happen here. So once there is lot of friction and the metal is moving, the chip is moving out like this. So what happens is there removes all the impurities and other things on the surface, and here it tries to increase the temperature, and the nascent surface of the tool comes in contact with the chip. So now you see very high temperature, high pressure, it is moving on. Now you have to take the analogy of welding. So welding happens here. So when the welding happens here, it is a built-up edge which is getting formed on top of the cutting edge. So moment it is formed, it is called as built-up edge getting formed on top of a cutting tool. This built-up edge destroys the cutting geometry. So now the rake face, what was there, is now changed. The cutting edge will be shifted from the cutting sharp edge to some other point. So discontinuous edge with built-up, continuous chip with built-up edge is another phenomena which is seen. Tool chip friction causes the portion of the chip to adhere to the rake face. Built-up edge formation then breaks off cyclically, thus leading to half getting stuck on to top of the workpiece, half getting on along the chip. So the tool material will go along with the chip. The last one is going to be serrated chip. The serrated chips are those chips where you form alternative high shear zone, and then next high shear zone, and then we have a low shear zone. When there is a shear zone, this shear zone, the material will move through the shear zone and keep moving. So here you will try to have high shear zone and then in low shear zone. When there is an alternative of high shear and low shear zone formation, it will lead to serrated chips. So here you can see high shear zone strains. So here strains will be very high. Then in between the two high shear, it will have a low strain. So there is a tool associated with difficult to machine metals at high cutting speeds. We generate serrated chips. When machining titanium, it generates serrated chips. So or improper choosing of material, process parameter you might get. So this diagram clearly says, you can see here the chip is getting formed. So here is A. This is the shear plane, which we assume it as a plane, but generally it is a zone. And then this is phi. The workpiece is seen. So workpiece. So here we talk about the tertiary deformation zone, which is happening because of tool workpiece contact. Here it is secondary. So heat is generated, and generally what we do is we try to pour lot of coolant around it, so which gives you lubricating effect and cooling effect. So heat is dissipated here as well as heat is dissipated at the bottom. So primary deformation zone you will try to see here. So continuous chip formed in ductile materials like low carbon steel, copper, aluminum alloy occurs at high cutting velocity What is high cutting velocity? Pi d n, and low friction between the tool and the chip leads it. Produces a very good surface finish. The force is less, power is less. Chip breaker prevents them from getting chip entanglement. Continuous chip with the condition for continuous chip formation, ductile material, high cutting velocity, smaller feed rates and smaller chip thickness, larger rake angle, positive rake angle, sharp cutting edge, and proper choosing of cutting fluid and lubricant. Discontinuous chip, generally it forms in brittle material like cast iron, bronze, high carbon steel, occurs at low cutting velocities with high friction on tool. So, once there is a high friction on tool, the tool is going to get worn out very fast. So, low cutting velocity, larger feeds. Now, you can assume feed is along the axis, you give this, that is feed. So, large feed, high friction and low cutting velocities. So, leads to poor surface finish and reduced tool life. Shorter chip break are easier to handle and dispose of. Continuously it is long, it is difficult. So, the discontinuous chip falls on top of the on the pan which is there, chip pan collector. We saw during the or we will see when we study more about the lathe machine, we will see where is the chip getting collected. So, what are the conditions? It has to be a brittle material, low cutting velocities, larger feed, higher chip thickness. Higher chip thickness means T0 by Tc, higher chip thickness, and then high friction, inadequate cutting fluid, rough and uneven workpiece surfaces are formed. What are built up edges? These are built up edges. As I said, there is a welding of the chip material happening to that of the tool. Formed in ductile materials at low and medium cutting velocities. High friction causes them welding operation on the rake face. It minimizes, can be minimized to use a sharp tool, but cutting speed, high cutting speed and proper cutting fluid can be used to reduce the formation of built up edge. It leads to poor surface finish and sometimes it forms a cover. So, moment it forms a cover, it tries to prevent the tool getting worn out. So, the conditions for continuous chip with built up edge: ductile material, low to medium cutting velocities, smaller rake angle, larger chip thickness, high friction and ineffective cutting fluid. All these things leads to continuous with built up edge. Serrated, the formation formed in difficult to machine material, titanium alloy, austenitic stainless steel. You can also have magnesium, you can have inconel. These are all difficult to machine materials. They has a sawtooth like appearance, which has alternative high shear strains and low shear strains, right? High shear zones and low shear zones. Occurs at very high cutting velocities. Difficult to machine material can be done. High cutting velocities are the condition for it. So, now how do we reduce it? We apply external heat so that the material is softened and you start machining. Thank you very much.